All right, so for the next couple of weeks, we're going to talk about transmission lines. We're just getting into it today. And our book does something really interesting and different compared to most, I guess, most treatments of transmission lines, which is that they begin by talking about transients on transmission lines at DC. So maybe with a DC excitation and a switch and things like that. But let's begin by talking about what exactly is a transmission line. It's just the conductors that connect your circuit together. So if I had a circuit that maybe looks like this, and some wires, and then maybe a load over here. You know, this is my source. This is my load. And this is a transmission line. They've never come up before in any of your classes because the assumption always was that the circuit is small enough or the frequency is low enough, or in general, you are uninterested in transient effects or everything is at steady state. So you don't really care about the time delay that it takes for your voltage and current from over here to get all the way over here. But as we learned last time, electromagnetic waves move at a speed that is not instantaneous. It's really fast, but it's not instant. And that has side effects. That means that the length of these wires right here is important, and it can actually matter for your circuit. So we're going to talk about how. First of all, I want to talk about what transmission lines look like. You've definitely seen them before in your life. They're all around you. They might be a coax cable where you have an outer conductive shield and an inner wire in the middle. And by coax, I mean coaxial because they have the same axis. That's a kind of transmission line. You could just have two parallel wires. Or you can have twisted pair. You can have parallel plate waveguide, which we talked about a little bit in some of our examples on inductance. You can also have some of the more, some things that are more common in printed circuits. So you can have something like microstrip, where you have a non-conductive substrate. I'm going to use two different colors for this one so it's easier to understand. And then you have a conductive ground plane on the bottom and a conductive strip on the top. So a microstrip transmission line looks like this, where that's a dielectric. And these are conductors. And there are even more kinds than that. There are a lot of different kinds that get used in printed circuit board geometries, especially. You can have coplanar waveguide, where you have two conductive strips on the same side of the dielectric sheet instead of on opposite sides. There's a lot of different kinds. But anyway, transmission lines are literally the conductors that connect your circuit together and their specific configuration. Usually, for something to be called a transmission line, it typically has constant cross section. And it also has to have two conductors, at least two. Two separate conductors, meaning if it's just one big conductor, like just the outside of the coax cable, or just a rectangular box or something like that, that would not be a transmission line. That counts as a waveguide, which is a more advanced electromagnetic topic for a different class. You can definitely still get waves to go down them, but they're sort of beyond the scope of what we're talking about today. However, transmission lines are important to your life and you need to know about them. Transmission lines describe not just the important effects that happen when the wires in your circuit are long compared to a wavelength, but they also describe things like how does crosstalk happen on like integrated circuits and other sorts of things where you have high frequency transients that are really close to each other. We're going to talk right now about this situation. An electromagnetic wave takes time to move. So let's say we have a DC source. We're going to name it VG for generator voltage, and it's also got a source impedance RG. You learned about impedances in circuits 2. If you forgot about them, might be a good idea to review them because we're going to talk about them a little bit for the next couple weeks. And then let's say that there's a switch next. And a transmission line after that. We're going to draw it as two parallel wires, but this is general and it could be any kind of transmission line. And then there's a load at the end. Just barely fits. All right, so what happens when this switch is closed? This is a DC voltage. And when the switch is closed, the electromagnetic wave takes time to get all the way down to RL. So at some point, like what happens in this transmission line before the current gets all the way to the load? This voltage doesn't instantaneously appear over here. It can't do that because, as we learned, electromagnetic waves take time. So remember that capacitor example that we did where we talked about why the capacitor can't support an instantaneous change in voltage? That's what we're going to do, because when you have two conductors that are separated from each other by some distance, that's a capacitor. This has a capacitance. And I was foreshadowing this in that midterm problem where I asked you to calculate the capacitance per unit length of some transmission line configuration. It has a capacitance per unit length. So when we close this switch, the charges in these conductors do move, but they move slower than the speed of light. In case you don't remember from last time, c is the speed of light. And it has a value of 1 over square root mu epsilon for reasons that we figured out last time. Have to do with the wave equation. So how is the current path going to be completed? Like there's going to be a current flowing here and there's going to be a current flowing here, but the current doesn't make it all the way down. So the current path has to be completed somehow. How can the current path be completed? There's a gap in the middle and the current's not making it all the way down to the end. And the charges, here, let's give this a definition of a z-axis, right? So this is going to be z, and right here is z equals 0. So the charges at z equals 0 would take a lot longer to reach RL than a wave. What happens is positive charges accumulate on this top line near the source end. And their fields repel positive charges in the line on the other side of it opposite this. So you end up with a net negative charge here. Sorry, those are minus signs. They just look like tiny dots. There we go. And this looks like a charging capacitor. A charging capacitor across which an instantaneous change in voltage has been applied. So that sets up a time-varying electric field. And a time-varying electric field means that we have a non-zero displacement current. Looks a little bit out of focus. Yes, that's about as good as it's going to get today. Well, that's what we get. So this displacement current is actually what completes the circuit. Positive charges, negative charges, displacement current in between them. Cool. Now the circuit is really only this long. The rest of all of this stuff to the right is not actually even involved in the circuit yet. But just you wait. This time-varying electric flux, this displacement current, gives rise to a time-varying magnetic field, which then gives rise to a voltage in like the next segment over, right? So we get a time-varying magnetic field that sort of circulates in between these two. Actually, it kind of goes around the top line and also around the bottom line. And then that's going to set up another EMF across the next section, and then the next section, and then the next section, and then the next section. Like we talked about last time, these electric and magnetic fields, when they are time varying, they link to each other like a chain, and the one generates the next one. So that helps the wave move down the line, and the wave moves at the speed of light, not at the speed of current, which is much too slow. So that's what happens. You end up with sort of a voltage, if this is like position, and this is voltage at some time greater than the time that we hit the switch, you're going to have a voltage wave that's sort of basically discontinuous. This edge gets sort of rounded out by the fact that the capacitor can't support an instantaneous voltage change in voltage. And then this wavefront moves down the line towards the load. Any questions about this stuff so far? Because there's more. All right, the next question is, how much current flows in this transmission line? We've said it's like a charging capacitor. So we've got our generator voltage here. We've got our generator impedance there. There's this transmission line that I'm just going to draw ... because I don't really care about the rest of the circuit right now. Before we know what this transmission line is connected to, how much current flows, right? What is I? This is a series circuit, except this is a transmission line. So what happens to this current? There's going to be some voltage across the transmission line. There's going to be some current flowing on it. And it's not an infinite amount of current. It is set by the relationship between capacitance per unit length and inductance per unit length. Which makes sense because this current comes from that interaction between Faraday's law and Ampere's law, which are based on the capacitance and inductance per unit length. The capacitance per unit length sets up displacement current. And this inductance per unit length sets up an EMF. So transmission lines have something called the characteristic impedance. Which we write with Z naught. This is a little zero. We use the word not to say it because there are some weird Britishisms in the roots of electrical engineering for reasons that no one really understands. And it is just the voltage divided by current for one wave going in one direction. Transmission lines can support waves going in two different directions, but voltage divided by current going in one direction are always related by this constant Z naught. And in fact, Z naught is equal to the square root of the inductance per unit length divided by the capacitance per unit length. Usually people put little primes on here to show that they are per unit length quantities instead of lumped quantities. This characteristic impedance represents real power transfer here. This is not, it's not that there is no power. From the point of view of this circuit, if we were to replace this transmission line with some resistor, usually Z naught is a real quantity or pretty close to real, it would look the same. It would look like power is being delivered to this just like it looks like power is being delivered to the transmission line. But on the transmission line, it's not being dissipated in the conductors of the transmission line. Nothing is happening to it. It just continues going down the transmission line. So from the point of view of this side of the circuit, the power goes away. So it looks like a resistance, even though really it's power that is traveling. So it really only depends, and actually this is an interesting property of characteristic impedance. Characteristic impedance depends only on the geometry of the transmission line meaning its dimensions and stuff, and its materials. If you have a lossy situation, sigma matters too, but if it's lossless or close to it, it's really only epsilon and mu. And by geometry, I mean, like I said, dimensions. All right, so when a transmission line is propagating, when a wave is propagating down the transmission line, it has this relationship where voltage divided by current is equal to the characteristic impedance. But what if the load has some other impedance value, right? So on the transmission line, V over I is equal to Z naught. What if the load impedance does not equal Z naught? Let's take a look at this. I'm going to name, this is the voltage, and this is Z. And at some time after that switch is closed, the voltage kind of looks like this, and we have this wave front that's traveling down the transmission line. And it keeps traveling down, and it keeps traveling down, and it keeps traveling down. But then we get to the load. Let's say the load is right here. What happens is you have a reflection. And some part of the wave gets reflected back. So now we have a reflected wave front traveling the other way. The voltage across the load is going to be, let's say V1. We're going to name this height V1, the forward propagating wave, plus V2, the backwards propagating wave. This is the incident wave amplitude, and this is the reflected wave amplitude. That's what happens. In this situation, the load impedance looks like a boundary condition. And this reflection gets set up by the fact that the wave needs to obey Ohm's law at the load, but it also, the forward propagating wave needs to have V1 over I1 equals Z naught, and the backwards propagating wave needs to have V2 over I2 equals Z naught. Although I2 is flowing in the other direction, so I2 would be flowing to the left and I1 would be flowing to the right. The next thing we're going to do is figure out what these waves' relative amplitudes are. How can we figure that out? Before I get started on that, I want to pause again and ask if there are any questions so far. Because this is some new and different and kind of wild and crazy stuff. So if anybody is surprised, know that you're not alone and ask me what you got to ask.
You said displacement current over to the other line. Did you mean like all of it or just like a part of it?
All of what?
All of the current traveling through the transmission line.
I think I understand your question. You're asking if there is any part of the current traveling down the transmission line
Yeah, to the load.
keeps going down to the load instead of being completed by the shorter path through the displacement current.
Yes.
Eventually, the current does make it down to the load, but it is not carried there by the conduction current because conduction current is too slow. So when we have this situation, here's my switch. It's being closed right now. And then we have this transmission line. Give them some thickness so you can tell they're transmission lines. The conduction current that would flow all the way down the line and over to the load and then back around is way too slow compared to the displacement current. The displacement current is sort of modeling the fact that charge is building up here and here. It's accounting for this charge storage. And then this displacement current, since charge is building up here, this displacement current allows charge to build up on the other side. Well, technically it's the flux integral, so it's the time derivative of the electric flux would be a better way to write that. Eventually, current does reach the load, but the current that reaches the load is sort of induced by many successive cycles. It's not as though they're discontinuous and there's one cycle and then another cycle and then another cycle, but it's induced by this process of displacement current and EMF and displacement current and EMF propagating down the transmission line. The current that flows on these wires and the voltage that's induced across these wires is sort of a secondary phenomenon compared to the behavior of the electric and magnetic fields between the wires. And the fields between the wires are really what carries the energy. Hopefully this helps. So the current moves at the speed of light down the wire, but not because conduction current is that fast, but because it is being induced that fast by the electric and magnetic fields that are moving down the wire.
Okay.
Okay, hopefully that helps. These are difficult and almost philosophical questions, but that's a really good one. All right, so we want to figure out what's the deal with this reflection. At first, our circuit looks like this from the point of view of the source. We've got our generator and its generator impedance, and then we've got the load just looks like it is the transmission line characteristic impedance. So this is a simple voltage divider. In your book, they use V1. I'm used to using V plus for this. So if I sometimes use V plus, just let me know that it's supposed to be V1 or remember that for yourself. But V1 is going to be the incident wave. And that's the amplitude of the wave that is just traveling down the transmission line towards the load, but hasn't reached the load yet. The transmission line just looks like a regular impedance whose value is Z naught. So V1 is going to be equal to the generator voltage times Z naught divided by the sum of these two things, Z naught plus RG. But then when it reaches the load, some other stuff has to happen. The voltage across the load is the sum of the forward going voltage wave and the backwards going voltage wave. So we've got V1 plus V2 there. And the current at the load, the current that is actually flowing through the load, is equal to I1 minus I2, because these two currents are going in opposite directions because the two waves are going in different directions. But we also have these relationships where V1 over I1 has to be Z naught, and V2 over I2 has to be minus Z naught because of the sign convention, because they're in different directions. And we know that VL over IL has to be equal to whatever the load impedance actually is. So since that's true, and we wrote down these other equations for VL and IL, that's equal to V1 plus V2 divided by I1 minus I2. But I1 and I2 are related to V1 and V2. So we can write this as V1 over Z naught minus V2 over Z naught. Okay. Let's define a new variable. We want to know how much of the incident voltage wave is reflected. So we define a new variable called the reflection coefficient. This is a capital gamma. And it is called the reflection coefficient. I'm going to put a subscript L on it to indicate that it is the load reflection coefficient. And its value is V2 divided by V1. So then if I put this load reflection coefficient into this equation, I can write it as V1 plus gamma V1 on the top, and V1 over Z naught minus gamma V1 over Z naught on the bottom. And that whole thing has to be equal to ZL. Now I'm going to do some multiplying and some algebra, and it'll all be very fancy. You can see how in both of these terms we're dividing by Z naught. So dividing by Z naught on the bottom of a fraction is the same as multiplying by Z naught on the top of the fraction. So we can get rid of that stuff. And then I can take this denominator over here and multiply by it. So then I have V1 minus gamma V1 like this. So far, so good. And every term has V1 in it, so I can just divide through by that. And if I do that, I end up with C naught times 1 plus gamma equals ZL times 1 minus gamma. Oh, gamma L, excuse me. And here I want to solve for gamma. So I'm going to collect all the gamma terms on one side and all of the not gamma terms on the other side. So I end up with gamma L times Z naught plus ZL, because I've got this term and also this term, is equal to ZL minus Z naught. And if I divide everything through, I end up with the load reflection coefficient is the load impedance minus the characteristic impedance divided by the sum of those two impedances. And this is the relative amplitude of the reflected voltage compared to the forward-going voltage. The reflected wave travels back toward the source, and it has the same relationship, so it's still got V2 over I2 equals Z naught, but with a minus sign because of the opposite direction of I2. And here's a cool thing. If the source is not matched, another reflection occurs at the source when the reflected wave hits it, and it goes back the other way. This was a whole lot of me talking, and it is time for you to do an activity. Here's the activity. Draw a voltage versus Z graph, like those ones that I was drawing earlier, for about 3 instants in time. So at least one before and one after reflection, for a characteristic impedance of 50 ohms and a load impedance equals 0, short circuit. I'm going to put you in breakout rooms and let you try this out. So just like I was doing earlier, I want you to draw graphs like this for a specific value in time. So t equals some value time, and then you've got a plot versus distance, and this is the voltage. And try to draw your forward going and backwards going voltage waves separately. So you might end up with something like this. And then you can maybe outline the total voltage on the thing by adding the two together. So it might look like that. Or if your reflected voltage was negative, then it would look like, I'll use my pink pencil for this, then you'd have V2 on the bottom, and your total voltage would actually look like that versus time. So here come the breakout rooms. Get ready to do this activity. And this is the one I want you to take a screenshot of. So be prepared. All right, welcome back, everybody. So you were doing an example where you have a transmission line whose characteristic impedance is 50 ohms and whose load impedance was 0 ohms. And I wanted to draw some plots, some graphs of voltage versus position at a few different times. So let's do that. Before the incident voltage wave arrives at the load, right? We've got V1 has some amplitude. I didn't give you a generator voltage or anything here, but the amplitude of V1 is just going to be VG times Z naught divided by RG plus Z naught. So let's say that Z naught and RG are both 50 ohms, and so V1 just becomes VG over 2. So then we have V1 propagating down the transmission line, and it's still on its way there. Incident wave. And it has height. That value is V1. When it hits the load, right, the incident wave front makes it all the way down to the load. And it still has height V1. The reflection coefficient is going to be the load impedance minus the characteristic impedance divided by load impedance plus characteristic impedance. So that is equal to -1. All right. So the backwards going wave, the one that's propagating back towards the generator, V2 is minus V1. So here's my backwards going wavefront like this. This is V2 on here. Which means if I look at the total voltage on this transmission line as a function of position, it looks like this voltage went all the way down to the load and then hit the load and then started becoming zero as it came back. So it looks like it's doing this, and then this point where it is zero is moving back towards the load again. Which makes sense because eventually we should have it look like a zero impedance right at the input to the transmission line, because we're at DC and wavelengths don't matter yet. At time equals end, my voltage versus position plot just looks like zero all the way across. Whoops, I didn't. There, now you can see it. Any questions about this stuff? Brandon, let me know that the participation links are not visible. I will make sure to make them visible right after class. So anyway, that's what happens in this example. The incident wave goes down and then the reflected wave comes back and just directly cancels it out completely until it gets back to the input to the transmission line, and then you just have a short there.
When you drew the reflected V1 equals 0, what, I guess I'm understanding the convention, how you have it above the axis.
I'm sorry, what?
After the reflection, after V2 sort of cancels out V1 to equal 0 for the impedance, on the graph you drew, the dotted line, you have it above the.
This is the total voltage. So this is as it's going back, you still have V1 not equal 0 over here, and you have V2 equals minus V1 over here. So they're canceling each other out along this section, but over here, V2 hasn't made it this far yet. So the voltage here still looks like it's just V1. Does that make sense?
So that's like, okay, I misread it. And then the third situation, after it reaches the end, it's 0. Okay. No,
yeah, it's after they've both made it all the way down. Yeah. All right, so that was a cool example of this whole thing. And I want to talk a little bit, how long does it take for these reflections to occur? The wave velocity on the transmission line is 1 over mu epsilon, right? So it's like, I'm going to write VP because usually we only use C for actually the speed of light in a vacuum. So the phase velocity, 1 over square root of mu times epsilon. That's how fast these reflections happen. So then that time delay, which I'm going to write as tau sub d for time delay, is just the length of the transmission line divided by the phase velocity. And if we wanted, we could draw this in a little bit more of a time-based format. I'm going to show you how to draw a bounce diagram. What you do for a bounce diagram is you've got, this is a time axis. This is also a time axis. Across the bottom here is a position axis. So you've got z equals 0 for the source over here, and z equals wherever the load is over here. And then you separate this plot into stripes of the time delay it takes to propagate all the way down the transmission line. So the voltage at time 0 is just V1. And that propagates down until you get to the load. Then you have a reflection. Below this point, VL is just equal to 0 because no voltage has arrived here yet. Above this point, VL is V1 plus V2. And V2 is equal to the load reflection coefficient times V1. The voltage here at the source, at the input to the transmission line stays equal to V1 until we get to this point. But then this reflected wave gets all the way back. And if the generator impedance is not equal to the transmission line impedance, you can have another reflection here. So then the input to the transmission line voltage becomes V1 plus V2 plus V3, where V3 is the generator reflection coefficient times V2. And V2 is gamma L times V1, so it would be gamma G, gamma L, V1 for V3. And then once you get over here, the voltage at the load, oh, can't see that high. The voltage at the load then becomes V1 plus V2 plus V3 plus V4, because then you would get another reflection heading back that way, and back and forth and back and forth. These bounce diagrams tell you what's happening to the transient voltages on the transmission line. But there is an important thing to know about this. And I was going to do it in an activity, but I think there's not quite enough time. So I'm going to do it in one big group altogether. And that is, there's an important fact that you need to know about gamma. We'll talk more about bounce diagrams on Wednesday. Don't worry, you'll get a chance to draw some. They're fun-ish. The question I want to ask now is, all these reflections keep happening. Does that mean the voltage never settles down? Or do we eventually reach steady state in the system? How do we know? What is the absolute value of gamma? Well, for passive loads, the real part of the load impedance is greater than 0. And also true for transmission lines. In fact, Z0 usually has such a small imaginary part that we're going to say that Z0 is real for this example. It doesn't ruin anything if it's not, you still get the same result. So I'm going to say Z0 is approximately real. I'll set it equal to R0. All right. So, or a better way to write this would be the imaginary part of Z0 is approximately 0. And the real part of Z0 is greater than 0. This is true for both the load, for passive loads, and for the transmission line. So in that case, what we have then is I'm going to split the load up into R plus JX for the load minus R0 Here's our load reflection coefficient. Then we have RL plus JXL plus R naught. Let's take a look at the bounds of this problem. If let's say that R naught is some finite real number and positive. If RL is extremely large, let's let it go to infinity. We end up with RL plus some finite size small stuff divided by RL plus some finite size small stuff. So then gamma L would be 1. Let's let XL go to infinity and everything else be finite. We have XL minus some finite size small stuff plus some finite size small stuff. Same thing on the bottom. Again, gamma L equals 1. So regardless of how you achieve it, if you have an extremely large impedance, like an open circuit, your reflection coefficient becomes 1. I'll write that down. What happens if you have an extremely small impedance? Like what if this is 0? Or what if both of these terms are 0? Well, then you have minus R naught divided by R naught. So you get minus 1. So for a short, gamma L equals minus 1. What if you have RL is 0, but XL is some non-zero number? All right, so let's make that be 0, but these still exist. Well, then you have, these are two complex numbers with different phases, but the same magnitude, right? Because the magnitude of this top one would be square root of R naught squared plus XL squared. And the magnitude of this bottom one would also be square root of R naught squared plus XL squared, but they have different phases. So gamma L has magnitude 1, but it's at some angle phi. And if you don't have one of these three cases, you can see that gamma L might have some value other than 1, right? Eventually, you might not reflect all of the power from the load every single time. Like what if XL is 0 and RL is half of R naught, right? Then you have minus R naught over 2 on the top and 3 R naught over 2 on the bottom. So then gamma would be 1/3, minus 1/3. What I'm trying to show you here is that the magnitude of the load reflection coefficient is always less than or equal to 1. So when you're drawing these bounce diagrams, eventually all of these transients die out because you can never reflect more power back than you provided in the incident wave. You can never reflect more voltage back than you provided in the, well, yeah, you can't do that either. And so as a result, the transients all eventually die out as long as you have a passive system. That's our time for today. Next time, what we're going to talk about is everything here we did with DC. So we didn't talk about wavelengths. We didn't talk about the relative phases of the forward and backward going voltage waves. We're going to have some cool stuff to talk about Wednesday about that. But for today, what we were really focusing on is the fact that it is not instantaneous for the voltage to get from this end of the transmission line all the way to this end of the transmission line, and what are the consequences of all that. So hopefully you have learned something about that interesting topic, and I'll see you Wednesday. Thanks, everyone.